All right, so hi, my name is Kim. Thank you guys for being here. This talk is called IPVS for Scaled Private Cloud Load Balancing. I'll be talking about how we solved our load balancing needs for Kubernetes. I'll start with a brief introduction. I'm a systems engineer for Comcast VIPER. I've been with the VIPER group for about 4 years. I work on the platform engineering team, and we're responsible for the design and implementation of new infrastructure services for VIPER. And for the past 2 years, that has meant managing Kubernetes clusters in our lab and at scale in production. VIPER stands for Video IP Engineering and Research, and we manage IP video delivery. We're a small office based out of Denver, Colorado. This group started in 2010 with just a few people, and we've grown to over 200 people since then. What this group does is take the core products that Comcast offers and implements them in software and serves them as IP video. This is different from traditional cable services in that it's a unicast transmission. So we'll only deliver the video that a customer is currently watching, as opposed to delivering every channel to all customers all the time. So I just briefly want to touch on how and why we began to use Kubernetes. In mid-2015, VIPER was developing an application called CDVR, which is DVR in the cloud. The application requirements were pretty aggressive, with a need for around 300 gigabits a second of network egress. And at the time, the architecture had over 15 microservices. We also had really aggressive timelines, with a plan to deploy over 4 sites in 2016 and another 10 in 2017. And with our traditional deployment model, it was going to be extremely expensive and time-consuming to deploy. Kubernetes was going to provide us a flexible way to deploy this architecture that would ultimately include over 2,500 pods per site. So VIPER created an architecture with most of these microservices running in Kubernetes, and we ran with it. As we started to build out our Kubernetes clusters in the lab, container adoption grew rapidly, and it seemed that overnight we went from single tenancy to multi-tenancy. And it was really great that we were running so many things in Kubernetes, but not all of Comcast enterprise services were running in Kubernetes. And we needed a reliable way for these other services to consume a service that was running in our clusters. Also at the time, CDVR on its own had 3 points of ingress. And as number of tenants and applications grew, so did this number of ingress points. And we quickly realized that we were going to need to address ingress load balancing, and also in a way that made multi-tenancy more efficient. So what did we need out of this load balancer? We needed something that would support at least CDVR's 300 gigabits a second of egress. It needed to handle TCP and UDP connections. It needed to handle many connections, possibly over 1 million concurrent, and multi-tenancy. It needed to be configured rapidly and online with no downtime. And lastly, we needed a solution that was going to provide some governance. Most of our tenants are not data center operators, so restricting the pool of IP addresses available for load balancing was really important. We started looking for options. We looked at a lot of things and came to the conclusion that there weren't really many solutions for us. Any Docker or Kubernetes specific solutions either didn't exist at the time or were pretty alpha. We couldn't run with a layer 7 load balancer because it wasn't going to meet our requirements and our throughput requirements specifically. And most options didn't support online configuration. We ruled out any solution that was required to run on independent or separate hardware outside of the cluster because it would add a lot of infrastructure complexity and cost. So our quest for a solution landed us on IPVS. For anyone not familiar, it's a network load balancer that's implemented in kernel space. It provides online flexible configuration, supports TCP and UDP for both IPv4 and IPv6. And because the request routing is done in kernel space, it's really, really fast. We also chose IPVS because it was a known in VIPER. We already use it in production for most of our video applications, and we knew that it would support the use case. It was also the solution with the most reduced cost, the least amount of uncertainty, and the most likelihood of success. So a little bit more about IPVS. It offers a few different options for load balancing that I'm not going to go into here, but the fastest and most familiar to VIPER was direct reply. Direct reply lets us scale egress out to the sum of the interface bandwidth for all of our backend nodes, meaning that if I have 10 nodes with 10 gig interfaces, I have 100 gigs of egress. It works by enabling backend nodes to reply directly to the client instead of proxying through the master load balancer, where you might have a limit of 10 gigs. In this mode, the IPVS Master owns the VIP, virtual IP, and advertises that VIP to the router. All of the backends are configured with that VIP on its loopback interface. When a request comes into the master, the request destination MAC address is replaced with the MAC address of the backend and sent to that chosen backend. The backend node sends its reply directly back to the client, not through the load balancer. So in this mode, you can actually handle more traffic into the cluster than the IPVS Master's interface actually supports. But all this kind of amazing performance has a cost, and there are two main limitations. First, there's a requirement for layer 2 adjacency between the master and the nodes. So it limits you to the number of nodes in your cluster to a physical segment of LAN. Also, there's no disassembly of the packet header in direct reply, so you can't rewrite the destination port. And I'll go into the details of the implications of that a little bit later. But we had chosen a solution, and once we needed to get it running alongside of Kubernetes. So this is the Docker run command for our initial implementation. The container runs in privilege mode so that the VIP can be configured on the primary interface of the master and the loopback interface of the backend. In the master mode, IPVS ADM is used to configure the front end and port to listen on, and also configures the backends to route traffic to. In backend mode, the VIP just gets added to the loopback interface, and any inbound traffic coming in on the defined port gets routed into Kubernetes. You'll notice that all of the information here is explicitly passed into the container as command line arguments. So we had load balancing. Great. It worked and it scaled. But we quickly realized that this solution could only work for a single cluster, single application deployment. Why was this? Well, let's start with the fact that we didn't have the option to port forward with IPVS, which meant we needed to use node ports. IPVS could not listen on a standard HTTP port and forward to Kubernetes node port, which meant that whatever node port was assigned to the service that we were routing to, IPVS had to listen and forward on that same port. So this didn't really give us the flexibility that we needed at the time. We had some additional problems with this implementation. Since node ports are applied to the cluster across namespace, no two tenants could use the same node ports. And as it turns out, humans are pretty bad at being random, and a lot of our developers were very prone to choosing the same node ports for their services, and this caused a lot of collision inside the cluster. The easy solution to that, use some randomization that Kubernetes supports. But node ports can't be randomized if we wanted to ensure that a Kubernetes service didn't get a new port every time the service got recreated. When we needed to provide a reliable way to retrieve information from a known address and port. So developers, because of this, had to statically assign node ports to their services. In addition, we were seeing inconsistency in node port assignments for single applications across site. So we had to have specific configurations for each deployment. Another problem that we had was, since we were explicitly defining almost every field in the container, the infrastructure was really coupled with the application. And in order for the platform team to provide a layer of isolation, we wanted to abstract this configuration. And lastly, because we were providing explicit configuration to the container, we were giving up on the flexibility that IPVS provides out of the box for online configuration. So every time we needed to make an update, we had to restart the container, causing downtime of our load balancer. So we needed to improve this. We needed to implement something that addressed the problem of application coupling and static node to port, port to node port load balancing. So we had a VIP, we had a port on that VIP, and when traffic came into the VIP, where it went beyond that, we wanted to be defined by names. And for each service that runs in Kubernetes, we are provided with a namespace, a service name, and a port name. So this backend construct that was already so conveniently provided to us by Kubernetes was where we wanted traffic to the master to be routed to. So we decided to make this better, and we came up with something we call Kube to IPVS. Kube to IPVS uses Kubernetes and the Kubernetes API to store load balancer configurations and retrieve them when they change. It enables us to port forward. It enables us to add and remove backends from a list of backends. It enables us to load balance traffic into all of our Kubernetes tenants from a single distributed application. If you recall in the previous diagram, load balancing into the cluster was performed using static node ports. Using Kube to IPVS, we're able to receive traffic on an ingress port and route that traffic into a Kubernetes service without relying on any node ports. So to understand how we do this, we first need a little bit of primer about how kube proxy works with IP tables. IP tables works by chaining different rule sets together and matches those rules against an incoming packet. An incoming packet has metadata associated with it, such as a destination address. IP tables will compare the packet with the pre-configured rule set, and if the packet matches, we'll send the packet to a target chain. Kube proxy uses IP tables to route traffic bound for a Kubernetes service into an endpoint for that service. In a Kubernetes cluster, when a packet comes into IP tables on a kube node, it first enters the pre-routing chain. Pre-routing contains a chain called kube services that every packet enters. The kube services chain contains a list of rules that match on service IP address and destination ports. If a packet matches on a destination port address and port, it will be sent into the kube service chain specific to that endpoint. To that service. The specific kube service chain contains a list of endpoints, which correspond to pods, that are available to host the service. The chain will pick one of those rules at random and send the packet to the chosen kube service endpoint. Here, kube proxy sets a masquerade bit on the packet and destination nats the packet directly into the pod that's associated with that endpoint. If the incoming packet doesn't match on a service or port in the kube services chain in pre-routing, it'll attempt to match in the last chain in pre-routing that's called kube node ports. If the incoming packet matches a node port in this chain, it will forward to the specific kube service and that's associated with it and complete the rest of the flow through IP tables, ultimately getting sent to the pod. So what Kube to IPVS does is it injects its own service chain into pre-routing that bridges traffic bound for a VIP address directly into the specific Kube service chain for a configured service. This means that packets go into pre-routing, then into Kube to IPVS, where if they match a VIP and port, they get routed into the service. This approach is transparent to Kubernetes built-in service load balancing. So if a packet doesn't match an Kube to IPVS, it gets processed through the kube proxy chains normally. So how does this work with our IPVS container? For the backend service, the Kubernetes API is queried to get a config map that contains the desired Kube to IPVS configuration. The backend service adds the VIP address to the node's loopback interface. It also uses the config map to create the VIP to service mapping in the Kube to IPVS chain in IP tables. This mapping in IP tables generates the direct jump into the specific Kubernetes service chain. So in the IPVS Master service, the IPVS Master manages the front end and VIPs and ports that IPVS listens on. It queries the Kube API for the config map, populates the currently configured VIPs, and adds them to the list of front ends. For each VIP that the master finds in the config map, it adds that VIP to the primary interface of the node. The master also queries the API server for a list of available nodes to add to the IPVS configuration as backend servers for each of these front ends. So in order to maintain the list of backends, the IPVS master will query the API for a list of nodes in the cluster. It will filter the nodes and maintain the list of backends in the IPVS configuration based on node health. As you can see, the last node in the kget nodes is in a not ready state. And in the screenshot on the right, you can see that the IPVS master has ensured it's not in the list of healthy backends. The IPVS master service will also remove any nodes that are cordoned or unschedulable. And as you can see in the screenshot on the right, the list of backends is missing the .158 node. This is because the IPVS Master service is scheduled and running on that node. And when the IPVS Master comes up, it will check its own IP address and filter that out of the list of available nodes. As mentioned before, we're utilizing Kubernetes config maps to manage the IPVS and VIP state in the cluster. The config maps are deployed with a pool of IP addresses that are available for VIPs. We're also utilizing node labels and selectors to isolate load balancing on a per VLAN basis. So we separate the VIP pools by VLAN so that when a new load balancer is added, Kube to IPVS will only add that VIP to nodes that have the correct VLAN node label. And this is something that we do to address the layer 2 adjacency requirement of IPVS. The IPVS backends and masters watch the config map in the API and dynamically update their VIPs and IP tables rules as it changes. So we essentially have real-time configuration of our load balancer. So in order to operationalize the updates to the config map, we created a UI that developers or operating teams can use to manage their own VIPs on a per-site basis. This gives us the ability to run the config map in a secure namespace so that only the platform and data center teams can manage the pool of IPs available. The config map can be dynamically updated by specific teams for their load balancing needs without directly interacting with the underlying infrastructure. So this enables different teams to be responsible for their own load balancing. And I'll do a short demo of this in a little bit. So once we had everything running in our clusters, we inevitably ran into some integration issues that I want to talk through. So VIPER's been running IPVS since as long as it's been around, and even though we should know better, every time we deploy using a new method of IPVS, we seem to run into the ARP problem, and Kube to IPVS was no exception. We were running happily for a while when QA began reporting performance degradation during load testing. And in troubleshooting, we found that all traffic was coming into and going out of the same server. And more interestingly enough, it was not the IPVS master. And we immediately knew this smelled like ARP. So what was happening was a race condition where if the loopback address was brought up by a Kube to IPVS on any backend, it would announce itself to the router. If this timing happened before the IPVS master announced itself, its ownership of the VIP, the router would send all traffic destined to that IP address to the loopback interface on the backend node. And with IP tables rules being set, traffic never left that single node. So a quick read through IPVS's documentation led us to the familiar ARP rules, which made the loopback interface on the backends ignore any ARP requests on the network. It would also disable ARP announce when it came online. So this left the IPVS masters to own the VIP. The next issue we ran into was when we attempted to co-locate the master and backend services for IPVS. We were initially explicitly defining a set of nodes for the masters and a set of nodes for the backends, but we wanted to reduce the operational cost, so we tried running them on the same set of nodes. But when these services got scheduled on the same node, they conflicted. The VIP address was assigned to the primary interface as well as the loopback address. And similarly to ARP, the IP tables rules were set and traffic never left the node. So we devised a way for the master to advertise its presence and for the presence of a master to disrupt the backend service. So when a master came up, it opens a port that the backend servers would check. If the backend server receives a response on that port, it halts itself on the node, removes its VIP, IP tables rules, and ARP rules. If it does not receive a response, it continues running and loops continuously on this port check. So in our initial implementation of Kube to IPVS, we were relying on IP tables out-of-the-box functionality to make rule set changes. In this mode, IP tables uses xtables lock to perform an individual check and set for each rule that we wanted to create. And at the time, Kube proxy was doing the exact same thing. So in cases where we had hundreds or even thousands of services, Kube proxy and Kube to IPVS would fight each other over who owned the IP tables locking. And this contention resulted in neither Kube proxy or Kube to IPVS being able to make changes, and ultimately this resulted in Kube services becoming stale. So to resolve this, we switched to IP table save and restore. And using this method, instead of using thousands of requests for each change, a single request would be made every time a change was necessary. And lastly, once our developers started using Kube to IPVS, they began to facilitate communication between services in different namespaces using VIPs. And occasionally we would see requests from a pod to a VIP timeout. And we realized this was occurring when the pod that was making a request was scheduled on the same node as the IPVS master. And requests from the private IP of the pod were unable to reach the VIP on the node's primary interface. And the Kubernetes kubelet actually provides an option to run in hairpin mode to handle these edge cases. So as soon as we enabled that in the cluster, this issue was resolved. Okay, so now I'm going to do a short demo. Ignore my desktop, please. Okay, so we're looking at the Kube to IPVS UI here. This is a load balancer that's running in a VLAN that we call green in the Mythical's namespace. The service that we have configured here is Mermaids. The port name is HTTP, and the VIP on the right is listening on port 80. So let's take a look at this, what this looks like in the back end. Here I'm doing a watch on the IPVS ADM command inside of the master container. So you can see it's listening on 165 on port 80, and we have a list of backend nodes here. Below the bottom here, move this over. Oops, sorry. Pause this. So at the bottom here, these are the IP tables rules that are on the backend node itself. So for each service that we bring up, we have 2 IP tables rules. And this destination and port is the VIP address that we have configured in the UI. And this is the specific Kube service entry in IP tables where the VIP gets routed to. Up on the top right here is our config map. You can see we have a list of IP addresses that are in the VIP pool, and the configuration that describes the service that we configured in the UI. So this is name state, service name, and port name. You can see that we're not using any node ports here at all in our definition. So I'm going to add another service. I have a service called Unicorns that's running in this cluster. We're going to add some more mythicals. Port name HTTP. We're going to put it on VIP address 166 on port 8080, and we'll create this. So now our service is created in the UI, and we'll go back to the terminal. The master has automatically configured this front end in IPVS. The back end now has the IP tables rules for the Unicorn service that's running, and again, that's getting routed directly into the service chain for that service. And our config map was updated with the new service on the new VIP on port 8080. If we go to a browser and hit that VIP, you can see our unicorns. So now say we need to run this Unicorn service on multiple ports. If you need HTTP and HTTPS, for example. In this case, we don't, but so we'll use an admin port to simulate this. So we'll put it on the same VIP address, port 8081, and create that service. Or, I'm sorry, create that load balancer. So now we have 2 VIPs pointed at the Unicorn service on 2 different ports. And if we come back here, the IPVS Master has been updated with the Sun Proxy admin port. Our backend has the new IP tables rules configured. And I just want to point out here that the service on the right is the exact same service that it's getting routed to in the back end. So even though it's listening on 2 different ports, it'll route to the same Kubernetes service. And our config map is updated with the new service for the load balancer. Go to a browser, port 8081, more unicorns as expected. So let's delete, we're going to delete the 8081 service. And this is automatically removed from the IPVS Master and the backend and the config map. Oh yeah, so 8081 will time out, no longer exists. Not going to wait for that to time out though. So say we have another tenant in the cluster that wants to create a load balancer for its service. They're in the same VLAN, but they're in a different namespace called typicals. The service is horses. Port name is HTTP. I put them on VIP 166, and they also want to listen on port 80. So we'll create that load balancer. So now we have 2 services in 2 different namespaces, both listening on port 80. The master has been updated with the new ports for 166 address. IP tables rules are updated for our new service, typicals, horses. And our config map has also been updated. So we can go hit that in a browser, and there are our horses. All right, so that's the end of my demo. Are there any questions? Yeah?
I was just wondering if you've given any thought to integrating this with the Kubernetes load balancer services and whether that's useful or not.
Yeah, we are talking about it. We haven't started working on it yet, but it is something we're looking into. Any other questions? Yeah.
You're using config maps to configure your controller or IPVS?
Yep.
Did you do it for certified resources in another way, or is it not a requirement? Maybe you could create a certified resource for this, just create a group, or
Sorry, I couldn't hear
why
you.
do you use config maps instead of certified resources?
Instead of?
Third-party resources, certified resources.
Oh, we just wanted to keep it integrated in Kubernetes. It was the easiest thing to do. It was available to us pretty easily. So, Anything else? All right. Thank you, guys.